Hi, my name is Francis. I'm a high school sophomore from Denver, Colorado, and today I will be showing you how our world is bound together by chemical bonds. The material being covered is recommended for students 10 plus, which is generally 4th grade and above. And another thing to note is that this course is best understood after having watched my last video, which introduces you to the atom and the periodic table. You can find this on the Interns for Good website. So if both of these things apply to you, then stick around because we have a lot to learn. In a nutshell, this course will expand on what you have learned about the atom. This means topics like atomic charge and the role of protons, neutrons, and electrons. This will also cover the basics of chemical bonding, including types of bonds, predicting those bonds, the role of valence electrons, and the difference between a molecule and a compound. By the end of today, you'll have a strong understanding of why chemical bonds occur and why they are important. You'll also be able to identify different bonds, as well as predict which type of bond will form between two atoms. So, unlike my last video, this lesson is much more focused on the concepts of chemical bonding, and not so math heavy, which will be kinda nice. So let's start off with asking ourselves, what makes up our world? And when I say the world, I mean everything you could think of, either on Earth or very far away. What makes up the trees? What about the clouds and the grass? Or maybe something more complicated than that. What about cars, or our homes, or even ourselves? Well, if you said matter or atoms, then very good, that's correct. But we know that there are only 118 elements on the periodic table, while there are many more than 118 materials and objects in our lives. For example, when we try to figure out what trees are made of, it's not as simple as looking up the element tree on the periodic table because there isn't one. We realize that there is no element titled tree or ground or air or car. So how are those things made? To understand how certain materials can exist without being on the periodic table themselves, let's take a closer look at something we're all familiar with. This map shows every state's most popular Halloween candy. And since we all love some type of candy, wouldn't it be cool to know what our favorite is made of? Well, we're going to do exactly that. I definitely encourage you to look closer at the unique ingredients of your own favorite. But since this lesson is for a wider audience, we will walk through one ingredient that all of these have in common, and that is of course sugar. So we know that sugar is a main ingredient in all candy, but what makes up the sugar? There's no element sugar, so how could it exist? Feel free to pause and think about this for a moment. So now that you've had a minute, let's go through this together. We know one piece of really important information, that everything is made of the elements of the periodic table. So from this information, it would be logical and correct to conclude that everything that is not a pure element itself is actually a combination of multiple elements. This is seen very clearly when you actually see the structure of sugar. Don't worry about all of the fancy lines and shapes for now. Just recognize that sugar is a product of the pure elements, hydrogen, oxygen, and carbon, and that it takes many of these chains to make even one crystal of sugar. So how would we classify this structure? Well, there are two ways that scientists have come up with to identify things that are not just one atom of one pure element. These things could either be molecules or compounds. A molecule is defined as a group of atoms bonded together, representing the smallest fundamental unit of a chemical compound. This basically means that whenever two or more atoms of any element are bonded together, the new structure can be called a molecule. Something important to note is that a molecule can be made from atoms of the same element. So, for example, you can have a molecule of hydrogen that is simply two hydrogen atoms bonded together. This features how you can tell a molecule from a compound. A compound is defined as a substance formed from two or more different elements chemically united in fixed proportions. So the main thing to remember about a compound is that it actually must have at least two different elements bonded to one another, where a molecule could be made of just one element or multiple. For an example, let's try identifying these two chemicals as either a molecule, a compound, or both. Let's start with the one on the left. So what do we notice? We see that there are two different atoms represented by different colored and sized balls, and we can see that the atoms are bonded to each other from the lines connecting them. Since there are two different atoms bonded together, we can call this a compound. But is there anything else? Well, if we remember the definition of a molecule, it is just a group of atoms bonded together. So we can also say that that definition describes this picture. So this structure is actually both a molecule, and a compound. The thing we can take away from this is that every compound is a molecule, but not every molecule is a compound. So when in doubt, if you have a structure made up of more than one atom, call it a molecule and you'll be correct. What about the one on the right? Well, since the two atoms bonded together are the same, it must just be a molecule, because a compound needs at least two different atoms to be bonded. So now we've covered the two structures atoms can create when combined. The next thing we need to know is what holds molecules and compounds together. Well, if you remember our sugar structure and drawings from earlier in the lesson, we've noticed that the things connecting all of our atoms together are the lines. These lines represent chemical bonds, the core of this lesson. So in order to understand how chemical bonds work, we must first understand the importance of valence electrons. A valence electron is an electron that exists on the outermost energy level of an atom. For now, consider an energy level a place where atoms can exist around the nucleus. To better help visualize these levels, think of them like grade levels at a school, where first graders, shown as the first level or N1 in the drawing, are very close to the teacher, the positively charged nucleus. Second graders, while still close, are a little further away and growing less attached to their teacher. This pattern continues for each of the following levels, 3, 4, 5, and so on. So why are the ones on the outside, the valence electrons, so important? To understand this better, let's say we had two atoms. Firstly, let's try counting the number of valence electrons in each of these atoms. If you did this correctly, you should have gotten 3 valence electrons on the left and 1 on the right. Good job! Now, there is one new thing we need to understand about the attractive forces between electrons and the nucleus. As electrons move further and further away from the nucleus, the attraction between the positive nucleus and the negative electrons grows weaker. So, for example, if we look to the atom on the left, the two electrons in the first energy level are closer to the nucleus and are therefore more attracted to it in comparison to the valence electrons, which are further away. And the same goes for the right. The electron furthest away, or the one on the outside, will have the weakest link to the nucleus. This trend is the same for all atoms. The electrons furthest from the nucleus will always have the weakest attraction to the nucleus because of the distance. So valence electrons will always have the weakest link to their nucleus. And as we learned in my last video, electrons can move away from their original atom. So which electrons would it make the most sense to lose? It would definitely be easiest to remove the valence electrons, since they are the furthest from the nucleus. And going along with the school analogy, you could think of the valence electrons as the graduating class, which are moving away. In order to move, the valence electron must be so far from its nucleus that it is able to be attracted by another atom's nucleus. So a valid prediction we could make for these two atoms is that the lone valence electron from the atom on the right would be attracted by the positively charged nucleus to the atom to the left. Now, remember the lines on the sugar diagram, and that they represented chemical bonds, but we never actually knew what a chemical bond was? Well, this is it. A chemical bond is a link or force between neighboring atoms in a molecule or compound that is caused by shifting valence electrons. So whenever you see a line connecting two atoms, now you know that it means that there is some type of interaction going on between the valence electrons. Also remember that part about force is very critical and definitely should be remembered. Looking at the drawing of sugar from before can confuse you, and almost leads you to believe that bonds between atoms remain in the same position and act like a chain connecting the two. But this is not true. Bonds between atoms are caused by attractive and repelling forces between the valence electrons of each atom and their nuclei. And as we've learned, these electrons are always moving and hold energy, so therefore the bonds are always moving as well. There are two types of chemical bonds that we'll be looking at today, which are covalent and ionic bonds. We'll start with covalent. The main thing you need to remember about covalent bonds is that the participating atoms are sharing their electrons. You can remember this by relating covalent to cooperation, where both parties benefit. This is definitely an important note to get down, so get your pencil and paper ready. That is that covalent bonds are formed when two or more non-metal elements bond by sharing electrons. You might be asking, well, how do I know whether an element is a metal or not? Well, here's a very helpful trick I learned from my high school chemistry teacher. It's called the staircase. If you start at boron represented by B and continue to move one square to the pointed down to the right diagonally, those elements are the cutoff between the metals and nonmetals. Everything to the right of the black staircase is a nonmetal, and everything to the left is a metal besides hydrogen. So that's how you can tell. But if you need to identify a covalently bonded substance without a periodic table, you could just as easily do it by knowing the common characteristics of covalent substances. They are usually soft or brittle solids formed and have a low melting and boiling point. Some examples of covalent compounds are water and sugar. You may not think the water has a low boiling point because 212 degrees Fahrenheit is pretty hot to us, but when compared to the boiling point of other compounds, it's really quite low. Now on to the ionic bond. Unlike covalent bonds, electrons are not shared in an ionic bond because they're actually exchanged. Another key difference between the two is that ionic bonds form when one metal and one nonmetal bond by exchanging electrons. Usually the valence electrons from the metal are attracted to the nonmetal. You can tell that a substance is ionic because it will have a high boiling point and will be formed as rigid or brittle crystals. A common example is salt, but what a lot of people may not know is that a key ingredient in your toothpaste is ionically bonded together. There is a compound called sodium fluoride, which is made of one metal sodium atom and one nonmetal fluorine atom that acts as the main cleaner for your teeth. So as you can see, these chemical bonds are everywhere. Another way to tell if a bond is covalent or ionic is to find the difference between the two atoms' electronegativity values. Electronegativity does sound like a fancy word, and it can be hard to understand. But a simple definition is that an atom's electronegativity value is the tendency of that atom to attract a shared pair of electrons toward itself. Knowing what we've just learned about ionic and covalent bonds, if two atoms were covalently bonded together or sharing their electrons, do you think that there would be a big difference in each atom's ability to attract the electrons to the other? If you guessed no, then that's correct. If we think about it, if two atoms are sharing electrons, they must be near equally balanced, or else one atom would just take all the electrons from the other. So now what do we predict for the electronegativity difference in ionic bonds? It would be bigger, right? Since an ionic bond is an actual exchange of electrons, one atom must have a much greater ability to attract electrons than the other one in order for a complete exchange to occur. Through many experiments, scientists have determined a spectrum to help tell ionic and covalent bonds apart when you are given both atoms' electronegativity values. If the difference between the two is less than 1.8, the bond is covalent, and if it's greater than 1.8, it's ionic. Here is a periodic table that lists all the electronegativity values of the elements under their element symbol. Let's work through a practice problem using this table. We will be using the table salt compound for this example, which can be written with its element symbols as NaCl, indicating one sodium atom and one chlorine atom. First, we can use the table in the last slide to look up each element's electronegativity, which will be 0.93 for sodium and 3.16 for chlorine. Step 2 is finding the difference by subtracting the smaller value from the bigger one. In our problem, that leaves us with 2.23. And finally, we can reference the spectrum to determine where our value lies in relation to 1.8. And since our answer of 2.23 is greater than 1.8, we can determine that the bond is ionic. Good job! For some more practice, feel free to pause the video now and determine whether these bonds are covalent or ionic. You will need to refer back to the table that has all of the electronegativity values in order to do this. And just as a reminder, the F2 on the right just means that there are two fluorine or F atoms in the molecule. So now you've had a chance to do this, we'll go through the answers. You should have gotten ionic for lithium chloride because the electronegativity difference is greater than 1.8. If you didn't get 2.18 as the difference, you could try looking up the values again or checking your subtraction. For sodium bromide, you should have gotten ionic as well, because the electronegativity difference is greater than 1.8. And for the third problem, which may have looked a bit confusing, you should have gotten covalent, because the electronegativity difference is 0. You can also keep this note as a little trick. Whenever you have a molecule made of two of the same atoms like this one, it will always be covalent. So that wraps it up for Intro to Chemical Bonding. Here I've linked some more reading and practice resources that all add on to what we've learned today. I would really recommend clicking the middle link and taking the time to really understand valence electrons, because there's so much more to them than what we were able to cover in this short lesson. And with that, I'll end with a little bit about myself. I've lived in Denver, Colorado for all of my life and have always been really interested in chemistry, particularly those reactions involving, particularly experiments involving large reactions, as you can see on the left. As well as that, I've been doing a lot of robotics lately and enjoy coding in my spare time. Alright, that's all. Have a good time reading more about chemical bonding, and I hope to see you soon.